Hello everyone again and Bismillah. So in this video we are going to design a proportional derivative controller or a PD controller in order to drive or lead the given plant to achieve the given specifications. The rise time should be less than or equal to 0.5 seconds and the maximum overshoot should be less than or equal to 0.05, or in other terms it should be less than or equal to 5% of the reference. Now in order to achieve this, you may ask, why don't we just use a proportional controller to do that, only a P controller? Now, let's just keep in mind that in order to achieve this specifications, this specification, the rise time, we found in the previous videos that omega n should be greater than or equal to, I guess it was greater than or equal to 3.6, okay? And we also had, so this is what we have found before. Don't forget this, please. And we also had the characteristic equation of a second order system as s squared plus 2 zeta omega n times s plus omega n squared is equal to our characteristic equation, which is s squared plus 2 times 3.6, which is omega n, times zeta times s plus 3.6 squared. So this is our transfer function with omega n being 3.6 exactly. We chose 3.6. And in that time, we found zeta to be something like 0.417, almost, okay? This is what we have found before. Now, let's just look at this specification, which is the maximum overshoot should be less than or equal to 0.05. How do we translate this? We would translate it as, we know that the maximum overshoot from the literature of control, we know that the maximum overshoot is equal to e to the power of minus pi zeta over the square root of 1 minus zeta squared. Okay, this is the maximum overshoot. And this should be less than or equal to 0.05. Okay, now doing some mathematical tricks and manipulations, we may get that from this condition, zeta should be greater than or equal to this expression, which is the absolute value of logarithm of 0.05 over the square root of pi squared plus the logarithm of 0.05 squared. Okay, and this gives us that zeta should be greater than or equal to 0.69. Now, do you find or do you see the contradiction? This is what we get from the second specification, while this is what we get from the first specification, and this zeta is not equal to this zeta at all. Now, this is because we were using a P controller, a proportional controller, and now our new transfer function and our new characteristic equation, they are both gonna be different from what we have had before. So now the transfer function of the PD controller is written as PD is equal to Kp, which is the coefficient of the proportional controller, plus Kd times S. Now you can see that we have added an additional pole to the system, because this S is in the denominator and it's added as a pole to the system. I'm not gonna go to the details. I'm just doing some practical things in here. So you may inspect the effects of adding a pole and so on by yourself. Now, benefiting from this transfer function of the controller that will be added, we will know our transfer function of the closed loop system. So it's h of s, as we said before, it's equal to Cp over 1 plus Cp. And for the sake of simplicity and saving time, I'm just gonna write this immediately, which is Kp times Kd times S over S squared plus 3 plus Kd times S plus 2 plus Kp. Yeah. Now you may notice that we are also controlling the second pole of the system by adding this Kd into here, but I'm not gonna go into the details. Now the new characteristic equation of the system is actually written as, it's the denominator of the transfer function that we have already written, 3 plus Kd times S plus 2 plus Kp. And when we compare it to the standard transfer function of a second order control system, we can say that, omega n is equal to the square root of 2 plus Kp. because you know that this is omega n, so the square root of it, this is omega n squared, sorry, and this is the square root of it, will be equal to omega n. And from the specifications that we have got, this should be greater than or equal to 3.6 in order to achieve the needed rise time. And at the same time, I mean, not at the same time, sorry, this gives us that Kp, when we square both sides and, subtract 2 from the right side, we will get that Kp should be greater than or equal to 3.6. Okay? So by this, we have got the first coefficient of our PD controller, which is Kp. I mean, sorry, not 3.6. I guess I'm wrong at this. Yeah, it should be 10.9. Yeah, as we have got before, it should be greater than or equal to 10.96. This is the first term of our proportional derivative controller. And in order to find the second term, we will say that, okay, now 2 times zeta times omega n is equal to 3 plus kd. Yeah, we can see that this is these are equivalent to each other. And from this, we know that kd will be equal to it will be greater than or equal to, let me not put it in this, let me not put it in this way. Let's say that zeta is equal to 3 plus kd, okay, over 2 times omega, which is, omega simply is 2 plus kp, okay? So this is a simple, zeta is equal to 3 plus kd over 2 times omega n, while omega n is this quantity. So from here, we may, and this should be greater than or equal to 0.69, as we have found before, using the condition of the overshoot, of the maximum overshoot. So from this, we know that kd should be greater than or equal to 1.38 times the square root of 2 plus kp minus 3. And if we select kp now to be 20, for example, 20 is it's a reasonable number. This means that kd should be greater than or equal to 3.47 from my calculations. Now let's say that kd is 3.5. The transfer function, if kd is equal to 3.5, this means that PD is equal, this transfer function can be written as 20 plus 3.5 times s. So by this, we have found the suitable, presumably suitable proportional derivative controller to achieve the given characteristics in the question. And we will be simulating this in the upcoming video. Thank you for listening.